Howdy, and welcome to our first look at triple integrals. We just finished double integrals, so now it's time to move on to just adding a third, to moving into three-dimensional space. So most of what we do for two integrals, we just do for three. The noticeable difference is just the notation we use. Instead of a double integral over a region D, it's now a triple integral over a region E, evaluated of a function f of x, y, z, and dv instead of dA, standing for volume. So a simple integral might be over a box instead of a rectangle. So the box AB cross CD cross RS, x, y, z, obviously, would have the integral, just the integral from R to S, integral of from C to D, integral from A to B of f of x, y, z, dx, dy, dz. And once again, this is going to follow Fubini's theorem. So we can do these, you just work from the inside out, right? You do the innermost integral, then the second innermost, then the outer. We can reorder these. That's not a problem. We can reorder these in the same way we reordered double integrals. So quick question here. How many possible orders are there? So I'll give you a second to think about that. That's right, yeah, there are 6, unless you didn't come up with 6, in which case that's wrong, there are 6. Yeah, there are 6 possible orders, it's just 3 factorial. So, here's, at the bottom of this is just a quick example. Let's consider the box, -1 to 1, 0 to 1, and 1 to 2. Negative all crosses, obviously. And let's take a look at the function 3x y squared plus z. So we'll just set up the integral. So 0 to integral will work from dx, dy, dz. So the innermost integral is -1 to 1. Then the y is 0 to 1. Then the z is 0 to 2. If we integrate with respect to x, we get 3x squared y squared over 2 evaluated from -1 to 1. And this is actually going to vanish because it becomes, because 3x is an odd function, so it becomes an even function evaluated from -1 to 1, just cancels out. Or evaluated -1 and 1 rather, and it just cancels out. So this part's just gone. Bye-bye. And here that means we just have xz that we're paying attention to. So xz evaluated from -1 to 1 is going to be 2z. So now we have the double integral of 0 to 2, 0 to 1, 2z dy dz. So here we integrate with respect to y. So now we have 2yz evaluated from 0 to 1, which is just 2z. So now just the single integral from 0 to 2 of 2z dz equals z squared evaluated from 0 to 2 equals 4. Done. So rectangular integrals, just not a problem. It's just iterating in order. Amazing. So that's really not the interesting thing, right? Like this is silly. I could show this to any reasonable Calc 1 student, and they'd be able to handle it. This is not what's going to make triple integrals complicated. What's going to make triple integrals complicated is when we're working with things that are that create functions of other variables. So let's say that in the same way that we had a region D that might be defined like such that y is between some function of x, some first function of x, and some second function of x, we might have a region E where z is defined as being between some first function g sub 1 of xy and up to some second function g sub 2 of xy. And then that means that now it's bound by whatever the projection onto the xy plane is, which can then be done with a double integral, where we might say, hey, y is between two functions of x, and x just go, or x is between two functions of y, and then y just goes from, maybe this is like 2 to 5 or something. So so what happens here is we create something where we need to worry about setting z to be some function of x and y, and then maybe setting, you know, x to be some like maybe y to be some function of x, and then x is just between two constants. As I said, here in this example, it would likely be that x is some function of y and y is between two constants, just looking at the way this is set up, but hardly important. Actually, it's not hardly important, it's very important. But you know, there's a not a numeric example. So without loss of generality, which we often write just w log, this is what we would do. And the generality here is that this is only one of three possible types. Another one might be where y is between two functions of x and z. Another one might be where x is between two functions of y and z. Those are type 2 and type 3 integrals, respectively. So anyway, what this creates is something where my region, E, is, you know, all ordered pairs such that x, y are in some region on the xy plane D, and z is between these two functions. And this generates this integral, the double integral over my region D, evaluated or with on the inside, the evaluation from g sub 1 of xy to g sub 2 of xy of my actual function dz. So essentially, I'm doing an iterated integral, but I'm figuring out what z is first, and then once I've done that, now it's just a double integral. So we then can break apart d in the normal double integral way. So, you know, here I said maybe, you know, y is between, again, without loss of generality, maybe y is between two functions of x, and then x is just between two constants. I don't know why I said a, you know, y there. That should be, you know, a to b. So that's, you know, that's about all we need to that's about all we need to deal with that. So let's go ahead and take a look at just an example. And do note here that these functions should be chosen based on the convenience of creating functions. Like if we're having trouble creating a function, then we probably shouldn't choose a certain type. If it's easy to create a function in terms of z, then we should. If it's easy to create a function in terms, if it's easy to create, sorry, a function for z in terms of x and y, we should. If it's easier to create a function for y in terms of x and z, we should. So it really depends on what's easiest. So here's a quick example. This one's pretty simple. Let's just find the volume of the tetrahedron bound by x plus 2y plus z equals 2, x equals 2y, x equals 0, and z equals 0. Do note that when we look for a volume of a region, it's just the triple integral of dv. There's no function, right? It's just a function of 1. We'll get into what actually having a function there means in a moment. So here's, you know, our shape, which I've tried to draw as best I could. And so what happens here is z goes from 0 to the plane. So z goes from 0 to what z is equal to, which is 2 minus x minus 2y squared, or 2y, sorry, not 2y squared. Now what we have here is, that's great, that takes care of z, but we need to figure out what's going on with y and x. And here, I could have chosen either to put x between two functions of y or y between two functions of x. The problem with putting x between two functions of y is that it would create something where I had to split into two integrals. Y between two functions of x has no such problem, so let's do that. Here, this the base looks like this. It is this isosceles triangle. So what we end up having here is we say, hey, y needs to be between x over 2 and 1 minus x over 2. So that's what it is. And then x is just from 0 to 1. So now we just evaluate this integral, simple as. So deal with z first. If we plug it in, we get, 2 minus x minus 2y, dy dx. Deal with y now. Plugging this in gives us 2 times y, which I've already replaced with 1 minus x over 2 minus x over 2. Then minus x times y, which is the same thing, and then minus y squared, which is just going to be 1 minus x over 2 squared minus, x over 2 squared. Again, I dropped, it doesn't matter to my calculation here, but I didn't show the parentheses. Those should be there. So my apologies, should have shown the parentheses there, but I mean, the calculations are correct. What we have here is we have just the eventual integral from 0 to 1 of 1 minus 2x plus x squared dx. This becomes x minus x squared plus x cubed over 3, evaluated from 0 to 1, which is just 1/3. So there's our answer. It's got a volume of 1/3. Neat. Now let's take a look at a physical example. So here, what we'll do is we'll say, hey, the physical example of triple integrals is something along the lines of a total mass, or something along the lines of a charge density, or just a total charge, with a charge density, sigma of xyz, or a total mass with a mass density, or just density of rho of xyz. So here, mass is just equal to the triple integral. Mass of a three-dimensional shape is just equal to the triple integral across the region the shape is in of rho of xyz dv. So here, let's consider the mass of a region bound by x equals the square root of yz, x equals z, and y equals 4, which, for the record, is, I'm going to have to go to the correct place here. Get out of the damn way. Nope. Yep, there we go. Here's what we're looking at. So, don't worry about this. It did not take kindly to the square root, so I had to kind of flip the function. But we only care about what's going on in this kind of upper quadrant, in this upper, well, honestly, just this upper octant, the purely positive octant. It's the only one we really care about. So what happens here is I only really care about this region. So what I might see is that x is greater, there we go, that's a good vision of it. X is greater than z, but less than the square root of zy. So x goes from z to root yz. But then once I've done that, I need to figure out what's going on with z. And what we might see is that now that I've gotten rid of x, I have, there we go. This, come on, cooperate. I have this cross section. This is as well as I can do it. It would be nice if I could get it just one more tick up, but I can't seem to do that. But I have this cross section, this triangle essentially, and it is a triangle. Going from z equals 0 to z equals y. And the reason we know it's z equals y is it needs to be something that agrees with this. So what we have here is we plug in z equals x into this, we get z equals z squared over y. But then that just means the only way this is true is when z equals y, or z equals 0, but we're not focused on that. So z equals y here is the one we care. Well, we do care about z equals 0 too, but that works too. So z goes from 0 to y. And then y, finally, when all said and done, y is just going from 0 to 4. So this is kind of the shape we're looking at. So, what you can see if we go back to my notes is I say exactly this is x is between z and root yz, z is between 0 and y is between 0 and 4. So we end up with this integral. Again, the density here, by the way, I forgot to drop that in. The density I wrote to be xy. So here we just take the integral with respect to x first, then z, then y. We do them in an order that will properly eliminate variables. So x needs to go first, and then z is in terms of y, so it needs to go second. Y is in terms of constants only, so it can go last. So here I integrate with respect to x first, get x squared y over 2, evaluated from z to root yz. This gives me y squared z over 2 minus z squared y over 2. And so now we integrate, 0 to 4, 0 to y of that, dz dy. We integrate with respect to z, get y squared z squared over 4 minus z cubed y over 6, evaluate from 0 to y, which gives us the integral from 0 to 4 of y to the 4th over 4 minus y to the 4th over 6 dy, which is the same as, y to the 4th over 12. We integrate that, get y to the 5th over 60, evaluate from 0 to 4, which gives us 256 over 16, or over 15. Jesus. 256 over 16 is just 16. Sorry, too busy paying attention to that. So yeah, 256 over 15. And that wraps it up. This finds us the mass. This is indeed the mass of the shape that I gave you. So now if we wanted a center of mass, we could do this in the normal way. You just find the moment about, in the case of x bar, you find the moment about the yz plane, which is the triple integral of x times the mass density. Y bar is the moment about the xz plane, which is y times the mass density, and z bar is the moment about the xy plane, which is z times the mass density. All within triple integral. And we put these all over the mass, which is what we already found, 256 over 15, and this gives us a center of mass. So let's do one last problem where I actually show finding a center of mass. We'll find, just for the sake of the calculation not being terrible, we're only going to find one center of mass, not all three. But I've set up one more problem. And I've already kind of got it shown up a little bit here. Let's say that we're looking at the region bound by x equals y squared, x equals z, z equals 0, and x equals 1 with a density equation of just 4. So that's rho xyz equals 4. So here, if we look at what this region's going to create, x needs to go, or z needs to go from 0 to x. And then x needs to go from y squared to 1. And then finally, we get that just y goes from -1 to 1. And the best way to view this is this is just a parabola, which just is essentially a parabola that is just stretched out up and down the z-axis. And then here, x equals z gives us just the diagonal plane, x equals z, z equals 0 tells us that we want the flat plane that's just the xy axis, and then x equals 1 says all the way up until 1. So we're getting kind of like a tongue shape going off to like a point, essentially. I don't know how better to describe it than that. I can't really draw it. So So again, it's best to say that, you know, z is going from 0 to x, and then x is going from you know, y squared to 1, and then just y goes from -1 to 1, because that's what's going to create this parabola. So there are certainly other ways you could arrange it too, but this is by far the best. So now we just integrate in the normal way. So here, let's go ahead and complete this integral. So if we do the first integral, what we end up getting here is just 4x. And if we do the second integral, when we plug this in, and this is going to be, you know, dx dy. If we plug this in, what we're going to get is 2x squared. So we're going to get, you know, 2 minus y to the 4th. So, you know, that's going to be -1 to 1. And then this is just going to be, you know, 2 minus y to the 4th. Or 2 minus, I'm sorry, 2 minus 2y to the 4th, rather. And then it's as simple as integrating this, which gives us just 2y minus 2y to the 5th over 5. And that's just going to give us what looks like 4 minus 4/5, which should be 16/5. So there's our mass, 16/5. Now if we want the moment about let's do the moment about let's say the let's do this about the xz plane. Let's find z bar, because that'll let us kind of carry the z through immediately. I'm going to pull the 4 out this time just to make my life a little bit easier. So it's going to be the same exact integral, or the same exact boundaries, rather. So, you know, y squared to 1, and then 0 to x. But now I've pulled the constant for the 4 on the outside, and now we're going to have z, you know, dz dx dy. And now again, if we work this one out, what we're going to get is, you know, 4 going from -1 to 1, from y squared to 1, and then just going to be x squared, or that's y squared, x squared over 2. That's definitely a 2. So what we're going to get now is, if we plug this in, we'll end up getting what looks like 4 times -1 to 1 of, in fact, we're just going to make this, we're going to make our life a little easier here. We're going to pull out that squared, or we're going to pull out that over 2. Make that a 2. So we're just going to get, x cubed over 3. So we're going to get 1 over 3 minus y to the 6th over 3. And then finally, we just go ahead and, integrate this with respect to y. And we're going to get 2 times y over 3 minus y to the 7th over 21. And that's just going to be, looks like 2/3 minus, yeah, it's going to be 2/3 minus, excuse me, 2 over 21. So 2/3 minus 2 over 21 is the same thing as 12 over 21. So we get, 24 over 21. But then our actual center of mass is going to be the moment about the xy axis over the mass. So that's going to be, this is, for the record, by the way, the same as 8/7. And that's just going to be, there we go, fix that. This is just going to be 8/7 over 16/5, which is going to be the same exact thing as saying that this is going to be, looks like 5 over 14. And there's our center of mass for for Z. And we would solve any other center of mass in the exact same way. So we just need to complete 2 integrals and then just put, the result of one over the other, and we get a center of mass. So yeah, that's it. So this is kind of as much as we care about with triple integrals for the moment. We'll deal with, converting to cylindrical and eventually spherical coordinates soon. But for now, this is enough. So until next time.